In this video, we're going to look a little bit closer at the solution to the harmonic oscillator differential equation, interpret what it actually means, and come up with several different ways in which it can be written. So just to summarize what we did in the last video, we had the harmonic oscillator, which we can represent as the mass in a string as the canonical example. We found that its equation of motion is x double dot equals minus omega squared times x, where omega is the square root of k over m. That's the angular velocity, or the angular frequency of the oscillator. We can write the solution to this on the following form. This is a second order differential equation, so we'll get two constants of integration. So we have that x of t is b1 times cosine omega t plus b2 sine omega t. Or we can write it as a sum of two exponentials. The first one is e to the I omega t. The other one is e to the minus omega t, multiplied by the appropriate constants. So let's begin by looking briefly at a couple of different cases here of the motion for different choices of b1 and b2. Basically, what you have is that b1 and b2, their choices corresponds to different initial conditions of the oscillator. So let's first take a look at the motion of the oscillator here. We'll pick the energy level here, and then we know that we have the amplitude at the turning points here when the energy is completely potential, and the object will then oscillate back and forth between the two turning points. Now let's say that we start out with the initial position being at the amplitude A here. That means that there's no room for any kinetic energy, so the initial energy is 0 when you start out. Let's see how that corresponds to what values of b1 and b2 that corresponds to. So first, we realize, of course, that x at time 0, that's x naught. That's going to just be b1, right? Because sine of 0 is 0, cosine of 0 is 1. Then let's find an expression for the velocity as a function of time. We just have to take the time derivative of this expression. So that becomes minus omega b1 times sine omega t plus omega b2 times cosine omega t. So v at time 0, v0, is therefore equal to omega b2. So that means that under these conditions, we start out at a and v equals 0. Well, then b1 equals a and b2 equals 0, so that the solution is a times cosine omega t. Another possible way you can start the oscillator is by keeping the oscillator here right at its equilibrium position, by giving it a little kick, so that at time t equals 0, its position is 0, but it has some initial velocity v0. So now we have x naught equals to 0, and we have v naught not 0. And just looking now at our result down here, we can see that, well, that means that b1 is 0 now and b2 is not. So we now have the result that x of t in this case is v naught over omega times sine omega t. And we can, of course, represent any other combination of initial positions and speeds by picking the appropriate values of b1 and b2 from using this method. Another concept which is important to understand when you're working with oscillators is the period. So the period is the time it takes for the oscillator to get back to its to its position and velocity that it had at a given time. So you can think of it as the time between returning to a given configuration. So if we look at the solution here to the harmonic oscillator, we can see that it repeats over time. And what we're going to do, we're just going to pick a couple different times here. This is t prime, and then one period later it's going to be here. This is time t. So you can see that this is now the oscillator returning to the same configuration. That is not the same thing as returning to the same position, because the oscillator has the same position at this position too, but it's moving in the opposite direction. So by same configuration, I mean that both the position and the velocity of the oscillator is the same. Now this is described by cosine and sine functions, and they have a period of 2 pi. So that means that if I take sine of omega t, or for that matter cosine of omega t, and set that equal to cosine or sine of omega t prime, then that's the same thing as saying that omega t equals omega t prime plus some integer number of 2 pi. Okay. If we're looking for t minus t prime being exactly equal to 1 period, then n should be 1 here. So if we take omega times t minus t prime, it's equal to omega times the period tau. That's going to then be equal to 2 pi, which means we can say that the period tau is 2 pi divided by omega. Right? So this time distance here, t, that's the period. So that means that over here we can then write the tau, the period, is 2 pi over omega, or 2 pi times the square root of m over k in this case. Okay, so much for the period. We are now going to look at another aspect of these formulas over here. And to do that, I'm going to first draw a triangle here. The length of this side I'm going to call B1, and the length of that side is B2. I'm going to call this angle here delta, and I'm going to now suggestively say that a squared equals b1 squared plus b2 squared. So then the length of this side over here will be a, because this is now a right angle. So with this, we can now rewrite the solution for the harmonic oscillator in a slightly different form, which is illustrative, I think. So we have that x of t. We can rewrite that now as just taking a in front, and then we'll get b1 over a times cosine of omega t plus b2 over a times sine omega t. Okay. Now if we look at b1 over a, there, b1 over a, well, that's just going to be cosine of this angle delta. So we can replace it in here. And same thing, b2 over a, well, that's sine of delta. Now, you should know that, or if you don't, you can easily look up, that cosine alpha times cosine beta plus sine alpha Sine beta barely fit it in there. That's equal to the difference of the cosine of the difference between the two angles. So it's cosine of alpha minus beta, which also equals to cosine of beta minus alpha, because cosine is an even function. So with that, I can easily rewrite this as a times cosine of omega t minus delta. So we can write that now as another way of writing the solution to a harmonic oscillator. It's just a cosine of omega t minus delta. A here is the amplitude, and delta here is known as the phase, or actually the initial phase of the oscillator. And this is again just another way to write it. We have two different integration constants. Now it's alpha a, the amplitude, and this phase delta. So we now have three different ways of writing the solution to harmonic oscillator. But you would like a couple more actually, because this is such an important result. So we're going to next look at the solution as a sum of exponentials. So what we have then is that x of t, as you well know, equals c1 times e to the I omega t plus c2 times e to the minus I omega t. Now these exponentials can be written as a sum of a cosine and a sine. So this is just equal to then c1 times cosine omega t plus I sine omega t. And then similarly for c2, where this minus sign comes from the fact that the sine function is an odd function, so the minus in front of the omega t comes on the outside. Right. Now we'll group these together by real and imaginary numbers. And if you just look at the solutions over here, we can see that this is just equal to this here. It must be b1, and this must be b2. Right? So we get b1 equals c1 plus c2, and b2 equals I times the difference between those two constants. Okay, and then we'll just do a little bit of algebra. And this minus sign comes from the fact, of course, that this I times that I is minus 1. And then we'll do the same thing by taking the difference between b1 and I times b2. And this gives us okay, so let's now look at this. We have the constants c1 and c2. In order to ensure that this solution is real, they have to have this form. But this looks like c2 and c1 are complex conjugate of each other. In other words, c2 is the complex conjugate of c1. I'm going to call that c over 2, which of course means also that c1 is the complex conjugate of c over 2. So let's now write down what we have here. We have that x of t, and we'll replace c1 and c2 with these values. Now we note that the complex conjugate of e to the I omega t is e to the minus I omega t, so we can rewrite this as now recall that the real part of z can be written as 1/2 z plus z conjugate. And that's pretty much exactly what we've done here. So we get that x of t equals the real part of c times e to the minus I omega t. So that's another result. Right. Let's go up here, and just to be complete, we didn't actually put a box around this solution. So to be complete, we should, I guess. Right, but this is what we have. So we can now rewrite this on yet another form. Okay, so now we have the solution to the equation of motion for harmonic oscillator on 4 different forms. But we're not quite done yet. We'd like to write on even one more form. And to do that, we'll observe that from what we just found over here, C is equal to 2 times C2. So that equals B1 plus I B2. And just like before, we can write that in the following form. Okay, and this is still cosine of delta, and this is still sine of delta. This is now e to the I delta, of course. So we now have an expression for C. And that gives us a 5th form in which we can write a solution to a harmonic oscillator. Okay. There it is. So we'll add that one to our list here as well. So believe it or not, all these 5 forms, 1, 2, 3, 4, 5, are useful in their own ways. We'll see why we would like to use this complex format, even though, of course, the actual position is real relatively soon. It is in many ways simpler to work with. What I also like to do here, just to complete matters, is to write down the velocity as well as on a form reminiscent of these 2 results over here. So we have that the velocity is a function of time. If we just take the time derivative of this, that's minus omega a times omega t minus delta. So if you make some room over here, we'll see that actually if we take the time derivative of the exponential form here, we will also get that x dot, like v is x dot, is e times the real part of minus I omega times e to the minus I omega t minus delta. Now, if we have an imaginary number, like I times a, and we multiply that by minus I times I, that's a real number a. Right, so when we take the real number of minus I times a complex number, what we get really is the imaginary portion of it. So this also becomes equal to, therefore, omega a times the imaginary part of e to the minus I omega t minus delta. Well, we can write it over here and alternatively also all right. So that's those are all different forms you can write this on. You should be comfortable with working with any of them, and in different situations, different forms are going to be useful. In the next video, we'll take a little bit look at the specific meaning of delta and how to visualize these solutions.